Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to go over Section 4 for Aromatic Systems Part 1. In this video we're going to cover what's known as heterocyclic aromatic systems. Heterocyclic means a ring system that has, in addition to carbons, other atom types like nitrogen or oxygen or sulfur in the ring. Okay? And so that's what hetero means. They're non-carbon type cyclic systems. Okay, or they have atoms besides carbon in that ring system. Now, we're also going to talk about some properties like the acidity and basicity as well as polarity. These are all different trends that we'll learn about and how aromaticity influences these trends. And then we'll finalize this by doing some problems together. You know, I'll sign them for you, and then you'll watch me solve them with you. Okay, let's get started. So the heterocyclic systems. Now, if you saw the problem set that I did just before this one, then you already have a clue as to what's going on here. So let me give you the rule. We're going to declare it here. I knew it was a little premature, but it was easy enough. Here's the way it works. You can count a lone pair on an atom if it is not already double bonded. Now, here's what I mean. Let's say, for example, I have a ring system like this. We have a nitrogen here, and let's actually put a nitrogen right there. Okay, so this is a nitrogen in two places. Now, this has an H, and I wanted to decide, is this aromatic? So here's my example. Well, this is a heterocyclic system because it's not all carbons. There's a nitrogen here and a nitrogen there, right? So it's more than just carbon. So the first thing you want to do is you want to consider, do any of the atoms have lone pairs? And yeah, this nitrogen has a lone pair. By the way, it does not matter if you draw the lone pair outside the ring, on the right side of it, or in the ring. It doesn't matter. They all mean the same thing. Don't draw it 3 times. That's wrong. But where you draw the lone pair, it does not matter. Okay? So sometimes people think that if it's drawn in the ring, then it's used in the ring. But if it's out of the ring, it's not used in the ring. It wouldn't make a difference. As long as the atom does not have a double bond, that's the rule, then you can count the lone pair. Okay? So in this case, these are obviously double bond atoms, double bond atoms. This nitrogen has no double bond, so you can count its lone pair. Notice how this nitrogen also has a lone pair, but you can't count it, right? Because it already has a double bond. So the rule is you can count a lone pair on an atom if it is not already double bonded. That's the key. All right, and now you're seeing it. So what we have here for the checks, the first rule, is it cyclic? Yes. Is it fully conjugated? Yeah. Every atom, well, is it fully planar? Every atom is sp2. Nitrogen's not sp2 like this, but we know it's next to double bond, so it will be through resonance. So yes. Is it conjugate? Yeah, everybody could circulate electrons around. And does it follow Huckel? Well, there's 3 pairs, so the answer is yes. It has 3 pairs, 6 electrons. 4 times 1 plus 2 is 6. So this is aromatic. Do you see that? Now, again, the key here is that we could not count the lone pair here because it already had a double bond, this nitrogen, but this one we could. That's it. It's very simple. I don't want you to think this is complicated because it really is not. It's as simple as that. Okay? So there are a few other examples I could do with you. For example, we can have an oxygen, and we can have, let's say, a combination of a nitrogen and an oxygen. Okay? So here are 2 more examples. Now, these are example 2 and 3. Okay? So 2 more examples. Now, what I want to prove in each example, a little bit something different, but in this case here, what I want to emphasize to you is that this oxygen has 2 lone pairs. Now again, is the lone pair pointing outside? Yeah, it could. You could draw it just like that. You could draw it where one's outside, one's inside. It doesn't matter. Because where the lone pair is located in your picture on paper makes no difference. So don't think that you have to draw a lone pair in the ring. It does not have to be drawn that way. Okay? So this oxygen has 2 lone pairs, but the rule is you're allowed to count 1. See, you're allowed to count a lone pair, only 1 lone pair. So you could never count more than 1. Never count more than 1 lone pair per atom. Okay, because it's impossible for it to just like a triple bond, you're not going to have both pi systems going, pi bonds going. Same thing, you can't have both lone pairs flying around, only one of them. Okay, so what we do is we count 1 lone pair and then this right here, so that makes it into aromatic, right? This is going to follow all the rules. It's cyclic, it's completely planar conjugated, and it's an odd pair, 3. And so it follows Huckel's rule. What about this one? Well, here you have 2 lone pairs. Again, whether it's in the ring or outer ring doesn't matter. But for convenience, we tend to put it in the ring. Okay, now for this nitrogen on top, we have to count its lone pair because it doesn't have a double bond. Oxygen doesn't have a double bond. We can count one of its lone pairs. And what happens? Well, so if we count all this up, and everybody's conjugated, right? Each atom is either double bond or next to a double bond. So you have full conjugation. Everybody's planar. Okay? The problem is that this is an even pair. It's 1, 2, 3, 4. This is going to be anti-aromatic. And that's a problem. So this right here, because we have to count 1 lone pair and only 1, you can't count this other lone pair. So it's anti-aromatic. Now, it turns out, and this is something that you might not need to know. This is a little bit of a detail that really goes far into it. Sometimes you need to know this and sometimes you don't. Depends on the year, depends on the professor, depends on, you know, what they want to focus on. So the idea is that, remember how we said large ring systems can avoid being planar, big 8 or more? Well, it turns out that atoms with lone pairs, they can avoid putting a lone pair into the system if it makes it anti-aromatic. So we are either going to say that this is anti or non-aromatic. It depends upon the point of view. So it would never be both as an option if this was multiple choice. They would say one or the other. But I want to make it clear that because oxygen and nitrogen, they can lean themselves away from the center of the ring, they can force their lone pair to not be planar. And that's why it becomes non-aromatic. But if it was forced to be planar, like in a big ring system, when we say assuming it's planar, then it's anti-aromatic. Do you see that? Okay, make sure that's clear. The only atoms that can do that are the ones that are not carbon. If it's not carbon, then it can lean away from the middle of the ring and force itself to be non-planar. It doesn't put the electrons into the ring. Okay, I don't think you have to worry about that. Usually you don't. Typically you would just say this is anti-aromatic. Okay, just so you know. All right, now that covers this section here. Okay, so hopefully that's enough, and you'll see a whole bunch of examples as we go forward. The next thing I want to talk about is acidity trends. Now, the way this works is for acidity trends, I want you to think about the goals are always the same for the next few examples. The goal is the same. When I guess if a molecule loses a proton, will it become aromatic? That's really all we're thinking about. If yes, it'll do that. If no, it won't do that. Okay? So, for example, if I have, let's say, a ring system like this. So we have this cyclopentadiene. Now, I want to ask you, if I have a base, will I lose a proton? Is this more or less acidic than this right here? So, which is more acidic? Now that's the question I want you to consider. Okay? Now think about the logic. All right? Actually, let me show you a better example because we're going to do a problem just like this one. So let's say I have a 3-membered ring and then I ask you the same question. Okay? So now out of these two, if I was to lose a proton, I hope you recognize here's the allyl position, right? That's the allyl position. Last semester we learned all about that location. That is the carbon that is not double bond and it's next to double bonds. So it's sp3 next to double bond. That is an acidic location because of resonance, right? So if I was to pull an H, it would